Assalamualaikum and good day. So today we're going to start with chapter 3. So we're going to start with the introduction of the topic which is called as Laplace transform. So basically, what is a Laplace transform? So Laplace transform is just another mathematical operation. So the same way that you view subtraction, product, which is multiplication, integration, differentiation. So basically, it's just another mathematical operation. It's called as a Laplace transform. Like the same way that when we have integration, we have the integration sign, and when you differentiate, you have d over dx. So there is also like a specific mathematical operator for Laplace transform, and the Laplace operator looks like this. So the symbol is a curly L, right? And whatever that we want to Laplace transform is going to go into the curly bracket. For example, if I have a function f of t, and if I wanted to find the Laplace of the function f of t, so that is how the operation looks like in terms of symbol. Alright, so according to definition, how do we find the Laplace transform of a function? So what you do is basically you're taking a limit from capital T to infinity of the integral from 0 to capital T of the function exponential of negative st, which you're going to multiply by the function that you wanted to Laplace transform, and then the products are going to be integrated with respect to t. Right, so that is how the definition of Laplace transform looks like. Alright, let me give you a simple example. For example, let's say if I were to have a function which is f of t, and f of t is just a constant function of 2. Right, when I wanted to find the Laplace transform, all I have to do is replace my f of t right there. So I'm going to have Laplace of 2 is going to equal taking the limit from capital T to infinity, the integral from 0 to capital T, exponential of negative st multiplied by our function 2, and I'm going to integrate that with respect to t. And according to the integration rule, because 2 is simply constant, so instead of leaving it right there, so I can bring that to the front just to make it simpler for us. So I'm going to put it as a 2, the limit from capital T to infinity, the integral from 0 to t of the exponential of negative st dt. So basically all we have to do is integrate an exponential function. Alright, so here let me just copy it down, and now we're going to start integrating. So here bear in mind that our variable is going to be t. So here I have exponential of negative st, so meaning by s is simply a constant. So when we integrate exponential, I'm going to end up with exponential of negative st over negative s, and the lower limit value is going to be 0, upper limit value is going to equal t. And because our integration is with respect to variable t, when you substitute the lower and upper limit, so that will be substituted right here. So where the variable t is, we're going to substitute the upper limit first, for which t is equal capital T, minus, so the lower limit when t is equal 0. Right, so now let's start substituting. So I'm going to have 2 limit from capital T to infinity, and here when I substitute the upper limit, I'm going to have exponential of negative s capital T over negative s, this minus and this minus, so we're going to have a plus, and then I'm going to have exponential of 0 over s when I substitute the lower limit t equals 0. And of course we know that exponential of 0, that is simply going to be 1, so the second term I'm going to end up with only 1 over s. Alright, so how do we take the limit? So taking the limit from capital T to infinity, so simply means that, so what happened to this function right here as the value of t goes towards a super big value? So like you can actually get a grasp of what happened to the function by actually like putting a big value on this. For example, you can try, so what is going to be exponential of negative 100? What value will you get? Or exponential of negative 1000, or exponential of negative 10,000, and so on. Right. So if we were to have a look at the graph of exponential to the power negative, the graph is somehow going to look like this. So basically, right, so as the value of t goes towards infinity, as the value of t gets larger and larger, so what happens is that the function is going to go towards 0. So this is where our 0 is, right there. So it's going to go towards 0. It's going to go towards, converge towards, but it will never cross the value of 0. Okay, because even exponential of 0 is going to equal 1. Alright, so it's going to go the value of towards 0, but it will never cross the value of 0. So basically what happens is that, so when you take the limit from capital T to infinity of exponential of negative st, so this term right here is going to go towards 0. So therefore the first term is going to be 0. So therefore you can have 2. So when you take the limit, so it's simply going to be 0 plus, and the second function, there is no capital T right there, so therefore it's going to remain. So I'm going to have 1 over s, so therefore the outcome is going to be 2 over s. Alright, so when we Laplace a function f of t equal 2, so what happens is that the outcome is going to be 2 over s. Okay, but the good news is that you don't have to go through this process over and over again every single time we wanted to Laplace transform. Like I did this before when I was a student, because I am a maths major, but you guys are not. You guys are engineers. You just have to know how to apply this. And because of that, we have this table right here, which is known as the Laplace table. Okay, so where you can find the table, so this table is actually in your module, and I have actually uploaded this on Kalam as well. So you can just go over here, and this is the one, Miss Laila Appendix Final Exam, so the one right there, and just click on it, download it. So it's going to be very useful for you for chapter 3, chapter 4, and even chapter 2 as well, right? So it's actually appendix for a real final exam, and it looks like this. So the topic that we've discussed before, the formula for VOP, even the formula for Euler, and this is the table. Everything is just there. I really suggest you to download this, so that when you start your revision, or even when you're doing like you're going through chapter 3, so you can simply use this. You have to get familiar with this, so that later when during the final exam, you know where to find each of whatever that you needed. Okay, so let's go back to our notes just now. So this is how the Laplace table looks like. Alright, so basically, if I were to refer to the first one that we had right here, so Laplace of a constant 2, if I wanted to use the table, so all I had to do is refer to the first item right here. So let's first have a look at the table. So there's two columns. There are two columns for the table. So the first column is f of t, the function that you wanted to Laplace, and then on this side, this is the function f of s, the outcome of the Laplace transform operation. So it's going to be like this. So if you Laplace a function f of t, the result is going to be a function f of s. So notice the fact that there will be change of variable. So before you Laplace transform, your variable is going to be in terms of t. After you Laplace transform, everything is going to be in terms of s. So that is why the first column, everything is in terms of t. And on the second column, everything is going to be in terms of s, because what you did is you changed the variable. That is the Laplace transform operation. Okay, so there are a couple type of function that you can Laplace transform. So the first one is when you have a constant, so that a over here is actually constant, and according to table, when you Laplace a constant a, so the outcome is going to be a over s. So this is what happened over here. So let me write it here. So when you Laplace a constant a, so that is going to equal a over s. So which is why when I Laplace the constant 2 just now, so the outcome is going to be 2 over s. So that's how you use this. So this a, you replace right there. So my value of a is equal to 2, so it's going to be 2 over s. That's it. It's a very simple idea. Okay, so the second type of function is when you have t to the power of n. So if you have a look over here, so how do you know like which value you have to substitute? So the idea is leave s alone. So s is going to be the variable, but you have to substitute anything else that is not s. For example, here I have n, so I have to figure out what is going to be the n value from my function itself. So the function that I wanted to Laplace transform. And for this case, n is going to be the power of the variable. So how do we use this? Let's say if I wanted to find what is going to be Laplace of t to the power of 2, automatically here my n value that is going to equal 2. So that's my n value. So when I plug it into the formula, so I'm going to end up with 2 factorial over s to the power of 2 plus 1. I simply replace all the n values. And of course, this over here is called as factorial. You have a button in your calculator for that, use it. And this is going to equal 2 over s to the power of 3. So that is going to be Laplace of t squared. And you have the same goes for exponential as well. So the only difference between these two is that one is for exponential to the power of positive, one is for to the power of negative. So what happens is that it's going to be the opposite. When this is a positive, this over here is a minus. When this is minus, this is going to be a positive. So that will be the case for exponential. And for the case of exponential, what you have to do is you have to substitute the value of a. So where do you find the value of a? So that will be from the power of the exponential. So figure out what is going to be a value, substitute right there. That is going to be your Laplace transform. For example, if I wanted to find what is going to be Laplace of exponential of t, so what is my a value? So obviously here my a value is going to equal 1. And according to the table, so when I Laplace this, I'm going to have 1 over s minus a, which is going to be 1 over s minus 1. That's it. And then we also have Laplace transform for sine and cos again. So what you have to do is you have to identify the value of a and substitute right there. And how do you find the value of a? So that is going to be at the angle of the trigonometric function. So it's going to be the coefficient of t. There's only like slight difference between the sine and the cos. For sine you have a at the top, and for cos you have s at the top, right? So that is just the difference between those two. For example, let's see if I have Laplace of sine to t. So now my a value is going to equal 2. So therefore, I'm going to end up with 2 over s squared plus 2 squared. So that will be the Laplace transform. And then we also have these two functions right here. So basically, this is called as the hyperbolic function. So it's just a function of exponentials. So if I were not mistaken, like you can check that in the book, the definition is there. So cos of at is basically just exponential of at plus exponential of negative at over 2. So it's just a function of exponential. And for the case of sine, so it's got to be exponential of at minus exponential of negative at over 2. So that is the definition of sine at and cos at. And this over here, if you notice, I'm pronouncing this as shine. So there are multiple ways of pronouncing this. Like I had like a whole lot of different version of this. Some people pronounce this as being sine h. Some people actually pronounce that as hyperbolic sine. So that is the long name. But when I was a student myself, my lecturers used to pronounce that as shine. So like S-H-I-N-E. That. Okay, so I am used to the term shine. Alright, so there is not much different between sine and shine and cos and cosh. So the difference is just here. So for the case of sine and cos, it's a plus right there. But for the case of shine and cosh, it's a minus. That will be the only difference. Other than that, it looks pretty much the same. And the idea is still going to be the same. You have to identify the value of a. And then next you have this u function right here. What does the u stands for? So u stands for unit step function. So this is what it's called. It's called as a unit step function. So let me show you how does a unit step function looks like. So in terms of as the function itself, so it looks like this. For example, f of t is going to equal 1 from negative 1 until 0. And it's going to equal 0 from 0 until 1. And if I were to sketch, it's going to look something like this. So let's sketch this. So here goes negative 1, here goes a value of 1, and this is just a graph of a constant. This is constant value, gradient is equal 0. It's not going up, not going down, so it's actually gradient m equals 0. So therefore, f of t equal 1 is going to look like this. And f of t equals 0, that is going to look like this from 0 until 1. So why is it called as a unit step function? Step over here represents stair, tangga. So that's what I call as a unit step function. Where the difference between these two is 1 unit, so it's called as a unit step function. So when the difference is like it's not 1 unit, for example, it could be 2, could be 3 units. So it is no longer called as unit step function, but it's just simply called a step function. But if it's a unit, it means there's going to be 1 unit difference between the higher and the lower one. Okay, so that is unit step function. Alright, so then next we have this function right here. It's called as a delta function. Okay, let me show you an example of delta function. How does it look like in terms of the function? So it's going to look something like this. For example, I have 2 delta of t plus 1. So delta function is very important, especially in electrical engineering, because mostly it is used to model signal. So that is the application of delta function. And if I were to sketch it, somehow it's going to look something like this. Okay, so let's see, it looks something like this. So first of all, delta function is just a straight line, either pointing upwards or pointing downwards. So how do we know it's pointing upward or downwards? So that will be based on whether the delta function is positive or negative. So this one is a positive, it will be pointing upwards. How many units? It will be 2 units upwards. And where is going to be the position? So set this equals 0, so the position will be at t equal -1. So it's going to be on this side. So for example, it's a value of 2 right here. So it's going to be pointing out 2 units at t equal -1. Alright, so it doesn't necessarily that the delta function, it could be only one function. So it could be multiple, called as train of delta function. So a few delta function being combined together. For example, I can put also here minus delta of t minus 2. So here what happened is that for this one we know that the position is going to be at t equal 2 and it's got to be unit of 1 and it's going to be pointing downwards because it's negative. For example, it's 1 right here, -1 right there, so it's going to be somewhere over here. So there could be multiple of like lines pointing upward or downwards, and it's called a train of delta functions. So that is in terms of the shape. And for the delta function and also for unit step function, so what you have to do is you have to identify the value of d and just substitute into the function that you Laplaced on the second column. So all you have to do is identify d from here and substitute on the other side, and that's it. So that will be Laplace of the unit step and delta function. And why is it the last one is a negative value? Sorry, it's not a negative value, it's actually a value of 1, because here d is equal 0. So when I substitute exponential of 0, so that is simply going to equal 1. That's it. Okay, so that is why when you Laplace delta t, the value is going to equal 1. Okay, so now this is actually a couple of examples. So what happened when you Laplace transform, but basically I've shown you pretty much like everything when I show you the table just now, but like we can go through this together once again. Okay, let's start with the first one. So Laplace of a constant 10. So we have seen that before. So let's put the table side by side so we can actually see it and put it over here. Yeah, that is not what I wanted to do. So I am going to drag this. So I'm going to split this so the table and what we wanted is side by side. Okay, Laplace of 10. So I'm going to refer to the to the second row after the header. So Laplace of 10, that is going to equal a over s. Sorry, it's a over s. And my a value over here is equal to 10. So therefore this is going to be 10 over s. And Laplace of t, so here I need to identify my n value. My n value is going to equal 1 because it's t to the power of 1. So therefore this is going to equal 1 factorial over s to the power of 1 plus 1, which is going to give us 1 over s to the power of 2. And then here we have Laplace of cos 2t, and according to the formula, so I'm going to end up with s over s squared plus a squared. So what is my a? So it's going to be right there. So the angle, the number right front to the t. And so therefore I'll end up with s over s squared plus 2 squared, which is going to equal 4. And the last one here, the unit step function, I have to identify the value of d. So here my d value, that is going to equal 2. So I'll end up with exponential of negative s multiplied by 2, which is negative 2s, and that will be over s. Again, when you Laplace transform, you're converting the variable. So everything that is in term of t, so now is going to be converted to be in term of s. So that is the major reason for Laplace transform. Okay, now let's get back to this. And actually in the notes that I've prepared for you, that I prepared together with this video, so there where is it? So Laplace transform exercise that you can actually try. So where's the exercise? So here, it's here. So this is exercise, so try them. So I actually didn't provide the solution right there, but I don't think that I need to. So this is just very simple ones. I'm pretty sure you can go through this, but don't worry, I'll provide the solution later just in case you wanted to check it anyway. And let's go back to what we were previously talking about, right? So try that on your own and make sure that you are able to use the table. And before I've forgotten about that, let's have a look at this table again for this cases right here. So what I mentioned just now is when you have, like for the case of unit step and delta, so if you notice this is a minus and a minus. What happens if you have a positive one? For example, if you have u of t plus 2 and you wanted to find the Laplace transform of this, so what you will get then? So what you will get is that, right, so compare the left hand side and the right hand side. When this is minus as well. So therefore when this is a plus, automatically this is also going to be a plus. So you can have exponential of sd over s, and the same goes for delta. So if you Laplace delta of t, that is simply going to be exponential to the power of sd. So it's going to be positive as well. So it's going to be, that is not right. So let me write it again. So if I have Laplace of delta t plus d, so that is going to equal exponential to the power of positive sd. When this is positive, this is going to be positive as well. Okay, so that is how do you use the table. So next we're going to have to look at linear properties.